All right, morning everybody. I'm sitting down today because I'm extremely tired. The last day of AstroHackWeek.
Have you put up your phone?
Yeah, my phone is on the table over here, so it shouldn't interfere with the sound. That's for the people out there on the internet. Okay, so you'll need to, hopefully you've all Git pulled to get the latest version of the notebook. So we're now going to go carry on through straightline.ipymb. And if you haven't done that, you can do it now while I just remind you what we did yesterday. We were looking at a data set which had X values and Y values, and the Y values came with reported error bars. And we spent some time thinking about that data set and the assumptions we were going to make in order to fit it with a model. So we even got as far as deriving through all the probability theory that Brendon showed yesterday morning, deriving what the log likelihood function should be, what the log prior should be. In fact, I decided that because it's my prior. And then we went ahead and evaluated the posterior PDF, because the likelihood function is something you can calculate anywhere in parameter space. And the prior probability density function is also something you can calculate anywhere in parameter space. So if you can afford it computationally, you can make a grid of your entire parameter space, and you can just evaluate the unnormalized posterior everywhere as the product of the prior and the likelihood, the sum of the log prior and the log likelihood. Okay, so we did all that, and we got this picture that's now on the screen. This is the answer to our problem. I told you that for Bayesian, the solution to the inference problem of what are the parameters of my model given the data is this picture. This is the posterior PDF. Actually, this is an approximation to it on a coarsely sampled grid. But there you go. That's what you can't put in your abstract, so you have to summarize it somehow. And we talked a little bit about how you might marginalize over one parameter or the other and do something like take the median of the distribution, or maybe the credible interval that contains 68% of the probability, that kind of thing. Okay, so this worked in 2D. What are we going to do more generally? So let's have a look through this. So with higher dimensions, it becomes rapidly less and less feasible to do this gridding exercise. Exponentially more infeasible. So we need a better way of sampling the space. You can think of a grid as a sampling of the parameter space. It's a very simple-minded one. We put evenly spaced samples and then deal with those. But what if we could instead draw samples from this probability distribution, not at positions we determine, but instead cleverly where the density is highest? And in fact, wouldn't it be nice if we could just draw samples from the distribution? If we could write a random number generator that, instead of being a Gaussian function or a uniform function or one of these things that are supplied to us in Python packages, but was a thing that returned random numbers drawn from the PDF that we really care about, which is the posterior PDF. In general, that's a very hard problem, right? We can evaluate the posterior everywhere, but that's not the same thing as being able to draw samples from it.
Can I interrupt for a second and ask what the wireless connection?
The wireless is the same as yesterday. For anyone who's stuck.
Guest 140 Win Hosk.
Guest 140 Win Hosk.
Can you spell that out real quick?
Can somebody pair code that onto a piece of paper with Hog at the back?
Write it everywhere, right?
Okay, good. I'm just going to go ahead and assume that everyone is connected to the internet. You've Git pulled, and you're looking at a notebook.
Looking at the screens, I can see.
Well, I guess a lot of people are going to be furiously working on their hacks because they do have to produce something by about 4 o'clock this afternoon. So it's a difficult decision on the last day of AstroHackWeek. Like, do you hack or do you listen to the tutorial? But if you are interested in the tutorial, it's good if you can see a notebook at least. Even if you can't run it yourself, you should try and see someone else who's running it, because there are exercises to go through and you can work with them in a group.
That would be good. Can somebody spell the password?
RWINHOSK.
Yeah.
Just put it on the SLAC.
I'm trying to help people get on the internet. I can get on the internet. I have an account.
Hopefully the people out there who are watching on the World Wide Web also have problems with, internet and stuff, so they don't mind us fooling around with this. Okay, are we cool, everybody? There's a notebook somewhere within your field of vision that you can follow along on, and you can see the screen behind me. Okay, so we need to make, we're after a machine for drawing samples from the posterior PDF. The PDF that we care about, we want to make a random number generator that draws samples from that distribution. So the machine we're going to talk about is called MCMC, which stands for Markov Chain Monte Carlo. So Monte Carlo implies random number generation. Markov chain implies a special kind of random walk, where the next step you take in the random walk only depends on the place you were before. And it turns out that you can derive Markov chain with following very simple rules that will return you samples from the posterior PDF, or in fact the samples from any PDF. So you should keep that in mind actually. There are some problems in astrophysics where you need to draw samples from a distribution. And as soon as you hear the term, we need to draw samples from this distribution, you might think MCMC. Okay, so it's not a method that's limited to data analysis where the PDF of interest is the posterior PDF of the parameters given the data. MCMC draws samples from distributions. Okay, so if you want to read about the derivation of this, it's in many textbooks. A good place to start might be chapter 2 of my PhD thesis, where I explained to myself, aged 25, how the Metropolis algorithm came into being. So this is what we're going to look at here. So let's keep on going. Here we have on the screen the Metropolis algorithm for drawing samples. If I had a whiteboard, I could draw pictures for you to show you how this works.
You know the table next to you is a whiteboard.
The table. Oh.
They're all writable, if you notice. No whiteboards at this.
Okay. Maybe I'll use my hands to try and
There's also a
explain
whiteboard
what's
in
going
that
on.
room. You could be in a bubble. And those are also whiteboards back there.
Everywhere but where you are.
Yeah.
You've chosen the one.
And I can't stand up because I'm heavily wired and too tired to stand up. So.
I can see that.
Okay.
You could get somebody to turn that table.
I will mime like this for you what the Metropolis algorithm is doing. Okay, so here is the algorithm. You pick a starting point here in parameter space, and you evaluate the posterior PDF because we can do that anywhere in parameter space. So we do that. So this is our first sample draw with its associated value of the posterior PDF. Now we need to decide where to move next on our sort of random walk. And so we make a proposal. Right? The Metropolis algorithm is you make a symmetric proposal distribution, maybe a spherically symmetric Gaussian around here, and we draw a random number from it. Right? We can draw a random Gaussian number. And so maybe the proposal will take me to here. Okay, so this is my starting point. This is my proposed sample. It's only proposed because I don't know if it's any good yet. So I have to decide whether to accept it as a new sample from my PDF or should I reject it. So the rule is I accept it if either it has higher probability density than this point did. Right, you can see how that's good because we want to move towards regions of high probability. But we're not interested in optimization, we want to draw samples. So we don't always want to go somewhere better. Sometimes we want to move somewhere that's not so good, so that we sample the distribution. So if the probability here is less than the probability density here, we accept it with some probability. In fact, we draw a uniform random number between 0 and 1, and we ask how does that number, that random number between 0 and 1, compare to the ratio of this probability density to this probability density. And we accept it on the basis of that comparison. Now, if it fails that test, if the posterior or if the probability density here is so much lower that it fails that little probabilistic test, we go back to this point, we say, right, we'll stay here this time, and we write this one out again. So now we have two samples here if we reject this one. If we accept it, we go here. And we've made a move. And then we do it again. We draw a proposal sample from our spherically symmetric Gaussian. So we might go here. See, that's how this is now a 3D problem, excitingly. And then we do the same thing. We compute the probability density here, and we compare it with what it was here. If it's higher, we move. If it's lower, we move with some probability given by a uniform random number. So what the chain looks like then as it evolves is something like this. Okay, you see it? All right, thank you very much. So here it is in Python, much more sensibly.
Better than 2D, right?
You must have theater training.
I can't do 4D because I wasted the fourth dimension available to me by acting it. Okay, so here it is in code. So we start somewhere, and in fact this is out of date here because see where I said start in the center of the prior volume. Actually, what this sampler is doing is starting at the input value of theta. So Daniel said to me last night, hey, you should really let the user initialize the starting position because it's important. So we did that, and now this comment is wrong. So I'll just go ahead and delete that. And then now we need to set up an array where we're going to store our samples, because writing out these points in parameter space, those are the things we care about. So we need an array for our samples. And we're also going to want to keep track of the value of the density at each one of those samples, potentially. And for fun, we'll count our accepted proposals. Nice to know how well we're doing in terms of acceptance fraction. And now we'll go just a loop over the number of steps we're going to take. So we specify in advance in this algorithm how many steps we're going to take along our walk, usually something large, but not too large. And then start doing proposals. So here's the proposal step. Theta new is a new point in parameter space, and it's related to the old place by this Gaussian random number. That's the rand n call. And then we calculate the posterior, the new posterior at this new theta, where theta is the parameters. Okay, and now we have our Metropolis Hastings acceptance criteria. Here it is. If you stare at that long enough, maybe you can appreciate that what's going on the right-hand side is a ratio of probabilities, and then on the left there's a uniform random number, and we're comparing those things. Daniel wrote this piece of code, so if you can't see how it works, you should ask him. All right, so if we accept it, then we take the new position, and we add 1 to the number of acceptances, and then if we don't accept it, then we do nothing. But we have to keep in mind that that means we're going to write it out again. And so here at the bottom, we always write the current position of the Markov chain. We always write it out to the list of samples. And then we return the chain. That's all of our samples, sample parameter positions, and then the probabilities and the acceptance rate. Okay, so let's give it a go. We'll load that. And then let's look at what we have to do to run this thing. So we have a number of things to pass in. We have to pass in, here's the call down here. We're going to have to pass in a starting position theta. We have to pass in the prior ranges, that's the theta limits. We have to specify how big this proposal distribution should be. And I've been calling it a spherically symmetric Gaussian, but the things that we're sampling have units, so it's not really spherically symmetric. We have to specify how big a step to take in each dimension. And then the number of steps we want to take is something that we get to choose. So here's a not crazy place to start. It's at the center of the prior. A much better place to start could be something that uses some knowledge of the structure of the posterior PDF. So you should think about what might be a really good place to start some other time. Okay, so we'll put it in the middle of the prior ranges. Remember, we assigned a uniform prior for this problem, so I put it in the middle. And then we'll choose step sizes and see how these are small fractions of the prior ranges. And then I say, well, let's take 10,000 steps, and so we'll run this. There it goes. So we just took 10,000 samples from our posterior PDF. Okay, so now we should look at what we've got. So let's take the parameters out of our chain, unpack that, and then we'll make a plot of how the parameter values vary with time. So how it varies along the walk. So here we are. The y-axis, you see the gradient parameter and also the intercept parameter, and then the unlabeled x-axis is the sample number, 0 to 10,000. So you can see something interesting happens right at the start. We go from the starting position quite quickly to a different position, and then we sort of randomly walk around it. So this is a good result. Right? You can see we've moved from an uninteresting part of parameter space to somewhere that's clearly interesting, and then something that looks like a stochastic process with no sort of places where we're getting stuck for a long time, nothing like that.
I have an acceptance fraction of 0.
Yeah, so me too.
Does that mean our steps need to be larger?
You can divide by 0 in log.
So have you worked through all the rest of the notebook to get to the place we're in? Did you do that? Did you load in the good log likelihood as opposed to the bad log likelihood? Let's go back and remind ourselves more fully what we did yesterday. So if we go and look at our functions, here's our log prior and log posterior. But we also had a log likelihood. And this is the one I wrote. Do you remember me showing you this? It had a for loop in it where we went through every term in the product of the joint likelihood, multiplying the terms together like fools, and then took the log at the end, and I said that was a bad thing to do. It's bad because it gives actually the wrong answer. If you load in this one from straight line log likelihood pi, you see it's being done with numpy, and we're taking the logs analytically. You see in the return statement there's a sum over terms, sum over log terms, instead of a product of terms that we then take the log of. So you need to load this one in, and then I think it should work. So there you go. One lesson from that is, if you ever work with me on a coding project, you should remember this example and ask yourself the question, could this code be written in a more optimized way? The answer is almost certainly yes, because when I write code, I have in mind my future self that has forgotten everything that happened 6 months ago. So I write code that I can understand rather than works really well. Okay, so here are our traces. So this is a good result. A more rigorous test to see whether we've converged, that we really are drawing samples from the posterior PDF. There's a good one due to Gelman and Rubin that involves doing multiple Markov chains and looking at the variance of the parameters within that chain and comparing it to the variance of parameters across chains. And they worked out a good criteria for that. So I encourage you to go and read about that. Gelman-Rubin test. Foreman, Mackey, and Hogg recommend looking at the autocorrelation length in this plot. So you can read about that in which paper?
Well, it's described in MC.
In the MC paper by
Documentation and paper.
documentation of paper. So if you go to the MC website, EMCEE, in the documentation there, and I guess it's written in, is it in Goodman Weir? Or
I don't think so. Or they assume that is understood.
okay.
One of the reasons we advocate the autocorrelation length is you need it if you're going to compute the uncertainty of anything you calculate with the chain.
Okay. So for the people watching at home, Hogg just said you need the autocorrelation length if you're going to calculate the uncertainty of anything you calculate with the chain. That is beyond the scope of this lecture.
I know.
So
That by uncertainty there, what means the uncertainty that you're kind of putting error bars on your error bars at that point.
error bars on error bars, right? We're not
Frequentist.
right. We're not talking about uncertainty on parameters. That's the width of the posterior PDF. We're talking about the uncertainty on the width of the posterior PDF.
Based on the fact that you
No,
need a new
no,
error
no,
when-
not talking about that. No, samplers are used to do integrals. It's the uncertainty on any integral you do with the sample.
Right. So if you define the width of the posterior PDF to be an integral quantity, you will need the autocorrelation length to estimate the uncertainty on that uncertainty, because we're not computing a posterior PDF here. We're approximating it with a set of samples. Right, you can see how if we drew one sample, that would be a pretty bad approximation to the entire posterior PDF. Okay, so now once we've done this visual check, things look good, and maybe in future you'll do something more quantitative.
So something that was interesting to look at, because we're just looking at that plot, it looks like it's going all over the place, even though the acceptance fraction was low. So I sort of zoomed in on it to see that actually for a while it stays at the same position and then switches.
Interesting.
An interesting historical note is that for a long time my PhD advisor thought that it was called the Metropolis algorithm because these plots look like cities. But That's not true.
So actually, that's very instructive. Can you go up and remake that plot with an X range? Just set the X limit, but both for the top plot and the bottom plot. That was just a plot command, right? So just do. Can you just do?
No, I can't because it's. Ooh, yes, I can. This is a
So I
plot.
just did chain like 4,000 to 4,500 or something like that.
You can just set plot excellent.
I need one algorithm.
Flip Markov in 4,400, 4,100.
Okay, I'm not going to do this. Can I do the? Can I do the zoom in?
It's instructive though because it shows you that actually the chain it doesn't.
Here's something I can do fast.
Isn't moving.
I can't live code, but I can change parameters live. How's that? Is this what you want to see?
And they're flat at the same time, right? It either moves both parameters or neither in this
Yeah.
mode, which is an interesting fact about these choices.
Right. So for the people at home, we're appreciating the fact that this sampler has spent a long time in this position, and so is returning the same M and the same B for a large number of samples, and then it's moving. And that goes along with the small acceptance rate that Surab pointed out from the floor. Okay, let me just rerun this with 10,000 to do the
Can
next
you do
one.
this with an isotropic Gaussian?
Yep.
And one interesting thing is that your parameter space is very anisotropic. You have this very small range in M and this very large range in B.
Yeah, but the step size is different.
Yeah.
That's what I asked. Is it an isotropic Gaussian?
No, the step size is different in
It's
the.
different.
Yep. Okay, so where do we get up to? Okay, now let's look at the samples in parameter space, and we can overlay them on the gridded posterior that we made last time. And so here we are. So you might just be able to make out here there are some contours in black that we got from the grid. You see the pixels here, and then in blue are the samples that we've drawn, and they're sort of 10% blue with the alpha, so that you can see something of the pile up out here.
Oh, just do it with a hex bin.
Sorry?
Do it with a hex bin.
That's a good idea. You could do this with the hex bin.
And you'll see they get very dense.
Yeah. I'm not going to do that live. Okay, so for a better view of posterior
It
sample.
looks different though to me, Phil. There's a trail of points up to the left, up and to the left.
Yeah, that's true. Do you
What
see
is that?
these? What do you think these are? What are they? When did we take them? Right, they're the first ones. Yeah.
So if you'd only plotted the second half of your chain there, you think it would look better?
Yeah, I think so. It's as if so throwing away the first half? No, 30%, 10%. Who knows? Throwing away the early part of your Markov chain is a good way of making a nicer plot. So that period that you throw away, where you're not sampling the posterior, but you're doing something else, you're getting to the interesting part of the posterior, is called burn in, and I don't think it has a good general definition. Am I right in that?
It's related. Figuring out what to chop off is related to these convergence criteria and the autocorrelation time. So you have to chop off the first few autocorrelation times of your chain, like comfortably, say, 20.
So you calculate the autocorrelation time,
Take out the first 20.
take out the first 20 or so autocorrelation times, and then after that say, right, we're going to take these to be posterior samples.
But wouldn't the autocorrelation time only be properly defined in the piece that does not include the burn-in?
So ideally, you would remove it, recalculate the autocorrelation time, and check that you're still safe.
Right, so we're discussing procedures here for getting good approximations, and some of them, I guess, are protected by theorems. Some of them are.
I mean, all of
Not.
these. They are. Some things are, but whenever you're asking questions about the chain, statistical questions about the chain, you're always asking empirical properties of the chain. So it's very much in frequentist empirical statistics. So so one of the weird things about doing MCMC is if you really are a power user of MCMC, you have to learn your frequentist empirical statistics.
Yeah.
In order to verify your result. And this is one of the reasons why really everybody uses all of statistics. If you go in deep enough, you end up using it all.
This is also an interesting example, if you remember last night's debate, this is an interesting example of scientists switching modes and behaving like engineers. Right, because I'm making like an engineer here, right? I'm just coding something up, I'm looking at it, it works great, we're going to continue. Right? That's engineering behavior. Apologies to all engineers out there on the internet, but I think that's true, right? Engineers
That's
are...
how the landing gear on your plane were designed, that you landed, and luckily they didn't break.
Right, it works. In a load of tests, it worked, it was proven to work, and then they put a safety factor on, and as a result, the fraction of plane crashes is very small. So it's a good way to go if you want to just get stuff done. Okay, so that was visualizing just with a scatter plot, and in almost all problems, of course, we don't have the contours to compare with because we can't afford to calculate on a grid. But what we can do is we can draw contours based on our samples. So look at these points here. They're points on a plane. We can imagine making a histogram of those points. So the histogram in 1D is an approximation to the 1D marginalized posterior. And a histogram in 2D would be an approximation to the two-dimensional posterior. So let's go back over that again. I said to make a 1D marginalized posterior, we just take the B values from our chain and we make a histogram. That seems intuitive to me, and we're going to do it in a second. In fact, let's do it now.
Why is that an approximation?
Why is it an approximation? Why is the histogram an approximation to the...
Or the fact that you marginalize? I mean...
The marginalization integral in math is not an approximation, but the histogram as an approximation to the 1D marginalized posterior is. Okay, so let's go ahead and do it, and then we'll talk about it. So here I'm making sure that I have a fantastic package called Corner, written by Daniel Foreman-Mackey. And what Corner does is make plots like this. Right, so this is all 1 and 2 dimensional marginalizations of a posterior PDF that's been approximated with a set of samples. So these plots are incredibly useful for figuring out what's going on. They don't tell you everything, of course, because you're only seeing projections. In this case, they tell us everything because we only have 2 dimensions. But in higher dimensions, they only show you the projections. But still, you can get an awful long way in understanding what's going on by looking at this plot. Okay, so here in the bottom left-hand corner, this is the 2D distribution. You see we've still got the points here that came from burn-in, and that's because we did plot data points are true. I'm just going to go ahead and remake this with false, because I don't want to see the points. There are so few points in this particular chain that this is a much better plot. So these contours here are chosen such that they're computed from a histogram made of the samples, and then they're chosen such that those histogram pixels contain 68% for historical reasons and 95% of the enclosed posterior probability. So we made a histogram and we normalized it, and then made these contours and then colored them in for style.
Phil, can you plot just the last 5,000 points just for my benefit?
For your benefit.
5,000 colon. Just on the chain, just put square brackets 5,000 colon.
5,000 colon. And now you want me to put in true again.
Oh, I don't care about that.
Because you want to see them.
No, I just want you to do that. Damn it. Why does it, what, have you set the range? Oh, you're plotting it in the range, you set the range for prior.
Yeah.
The prior range.
Yeah. Because I'm interested in how much information I've gained from the data. I want to look at the posterior in the context of the prior.
That is a good way to show it. I agree. Okay, good. I'm done.
Okay, so you can see that even there's a few samples out here still. That's interesting.
Yeah, it's odd.
Yeah. Anyway, okay, so we were unpacking this. This is the 2D posterior PDF. And then I just made histograms of the samples, or rather Corner did for me, in the M dimension and the B dimension. So let's just take a few seconds to appreciate what's gone on here. We took samples in a multi-dimensional space, and then we made histograms just by pulling out the B values from that multi-dimensional space and making a histogram of it. So this is marginalizing over all dimensions other than B. and we did it just by pulling out one column and plotting it. So for me, one of the main reasons to characterize posterior PDFs with samples is because it makes marginalizing out the other parameters trivial.
Can I make a comment?
Yep.
This is because fundamentally this is because samplings are used to perform integrals. That is the purpose of a sampling.
Yeah.
And MCMC is a method that was designed to perform integrals.
Yeah.
So it naturally performs the integrals you want.
Yeah.
It also means that when you're reporting results from an MCMC sample, you ought to be returning results that are somehow integrals.
Yeah.
Like the mean of your posterior or the median of your posterior. Those are two things you get by doing integrals with your sampling.
Yeah.
And
So
it's not a good idea to say return the mode of your posterior because the mode is not an integral property, so it's not something that's created by the sampling.
So following on from this point you're making about sampling being designed to do integrals, the reason we're taking samples, it's interesting to discuss whether all inferences of interest are integral quantities. Are you ever really interested in the mode or any differential quantity, or are you always interested in
the debate last night were integrals.
That's right. All the quantities last night were
including
integrals.
all my expected utilities.
Right, expected utilities are integrals. That's right. In fact, John Skilling likes to say there are only two problems in inference. One is how to assign probability distributions, and the other is how to do integrals. Makes it sound easy.
Well, it's measure theory.
Okay, so up here, just last thing, you see Dan has kindly written the numbers that you might want to put in an abstract, although he may have overcooked the number of decimal places. But these are medians, and then the error bars are the difference between the desired percentile and the median. And so up here in the core, we put, quantiles he calls them. So we chose 0.16, 0.5, and 0.84. 0.5 to get the median for the central value that goes here in large font. And then the error bars are the difference between these two quantiles, these two quantiles. And you can maybe do the math in your head and see that the 84th percentile is of interest if you think that 68% is the right number, the right amount of probability to quantify. Okay, so.
The question back is.
Yeah, oh sorry.
Should we use mean or median?
Should we use what, sorry?
Mean or median.
Should we use mean or median? In this case, it wouldn't matter very much, right? Because it's so symmetrical that the median and the mean are similar. In general, it doesn't matter very much. You just have to say what you did, right? Because when you're writing an abstract and putting numbers in like this, it's a large compression of a lot of information, and so you're losing a lot of that information along the way. And so the best you can do, if you're forced to do this, the best you can do is to state what you did along with it. Now that makes it a bit clunky in the abstract, but if you really care about the readers, you kind of have to do that. I like the median. Why do I like the median? I like the median because it transforms well. That the function of the median of a distribution is equal to the median of the function of the, not the distribution, the function of the parameter that's distributed.
Only if it's monotonic, right?
Yeah. Yeah. Subject to some constraints which are reasonable.
And the median is invariant to like some changes to the.
But what I just said about the, if I tried to say that about the mean, it would never be true. But at least what I said is at least sometimes true.
No, just don't look at McPhee when you say things like that, because you have like math pedants in the room.
Oh right.
there are some quite.
Zero is invariant.
Zero. That's it.
Can we agree that the median transforms better than the mean? Okay, that one got the math mode nod of approval.
You can also show that if you come up with an expected utility for how bad a point estimate is. So a point estimate is, I'm just going to guess a number for the value of the parameter. And if you say that you care about the difference between your estimate and the truth squared, and that's the thing, that's how much money you're going to have to pay, is difference squared, then the optimal thing to do is report the mean. Whereas if the amount of money that you have to pay is proportional to the absolute value of the difference, then you should have said the median.
Mm-hmm.
In practice, you have to have a really skewed posterior PDF for that to be very good.
Yeah. One thing to watch out for, actually, while we're looking at this particular plot, is that in this case, the 1D median, which I chose to be this reported central value, the 1D median lies here, and the 1D median in the B direction is also here. So because of the symmetry of this distribution, the centers of the 1D distributions are also the center of the 2D distribution. But maybe you can imagine that if this was some kind of banana shape, that might not be true. And that if you were to take the position in two-dimensional parameter space, which was median M, median 1D M and median 1D B, that position might have very low likelihood. So you have to watch out for that. That's why you have...
true for the mean as well. In fact, there's no statistic you can perform on the MCMC chain that's guaranteed to itself be a location of high probability, except to take a sample.
Yeah, so you must say these are compressions of the 1D marginalized posterior.
But that seems to argue that the mode might not be so wrong, right? You take your sample with the highest probability and report that.
There are a lot of reasons that's a really bad idea, but I think it's beyond the scope of this conversation, but we could go there.
Mm-hmm.
Once you get to high dimensions, MCMC will never get near the center of your distribution. Like if you're at 20-dimensional, you'll never see the center of your distribution for deep mathematical reasons.
And the highest posterior probability point, which was suggested as a possible interesting thing to report, is also the point that is most likely to be overfitting the data. Okay. Right, now that you've seen this Metropolis sampler in action, let's try and break it. So with the people around you, spend a few minutes fiddling with the control parameters that we fed to the sampler. So that is in this cell here, where we set up all this initialization, the step size, the number of steps. Try fiddling around with that. Maybe you want to go inside the Metropolis code and try and break it in various ways, and remake the plots and get a feel for what's going on. So 5 minutes playing around, breaking the Metropolis sampler. Go. You'll need to talk to the people around you, of course, because not all of you can see a notebook. So meet your neighbors, say hi, look at the notebook together.
Poor performance or actually
Poor performance. Yep. Okay, a point of clarification. When I say try and break your toys, I don't mean in a trivial way with a hammer. I mean in interesting ways where you learn something. So we're not interested in things where the code no longer runs. We're interested in making plots that give you poor characterizations of the posterior PDF. Okay, go. Hello, Tina. We knew what thing were you doing? And which one are you doing? Oh right, I see the efficient log right here. You need to load that in. Uncomment that. No, uncomment that. And you'll see what I mean by adding. Now you have to hit it again. That's too idiot. Right, now we have it. This is what I mean by adding. NumPy sum. Now we always sum the log likelihood and the log prior. So here we're summing the logs of the individual terms in the product that make up the log likelihood. Well, what that means is I should comment that better. Yeah, you gotta hit that again. Nice, All right, everybody, playtime is over. Okay, so I'd like you to tell me once you've stopped talking about what you're doing and come back with your attention at the front. I'd like you to tell me what happened when you changed various things. So who did what and what happened? Let's have some suggestions. Rutger, what did?
Change the step size.
What happened when you changed the step size, Rutger?
If you make it smaller, then the chain acceptance rate goes up, and you can see more random walk. The autocorrelation becomes longer.
Okay, good.
And if you make it larger, the step size, then you can see the acceptance fraction go down a lot.
Okay.
Did you make a plot of acceptance fraction versus step size?
Okay, this is interesting. So when you went for a very small step size to get better random behavior, what did the posterior look like?
Well, if you were to plot the samples, which I don't have here at the moment, I looked at the trace plots. But if you were to plot the samples, you see more clunkiness.
More clunkiness. Did anyone do this? Put the step size way small?
Yeah, that's what.
Oh, look at that! Show that to the room.
It steps very slowly, and it's very dense.
Yeah. So inefficiency. Cool. That was a good way to break it. Anyone else did something interesting? Yeah.
I did the same, it never gets there.
It never even got there. Oh, yeah, a really small step size. That was a good break.
Increase the step size and make it run again and again and again.
Yeah, but that was a good way to thoroughly break the sampler. Okay.
If we look at that one again, it did this, right? We tried to change to start from the limits from one of the.
Start on the edge. You started from the edge of the
Yes,
uniform
and it did
prior.
the same thing.
Yeah.
Does that mean that the posterior has that shape somehow, or it just takes longer to convert?
Why does it move in that direction?
I think it goes into one of the wings. I think it goes into one of the wings of the Gaussian.
Right.
And it approaches from the
trivial
side.
function. So.
Yeah. So the Gaussian is well defined and non-zero everywhere, and so it's kind of following a particular path through. But it's an interesting shape there. I wouldn't have expected that shape. Show Hog that shape. It's like a dog leg for the people at home.
Because the steps are correlated.
What's that?
The two steps are correlated in your code. So
The two steps aren't correlated.
uncorrelated.
Uncorrelated, yeah.
So you
that's
follow
to go
the
follow one to the
steepest-
end, and then
steepest-
So it preferentially goes in one
yes, and
proposal direction, and
while
then
if you have the correct steps, it goes straight to
good. So it's following the shape of the proposal distribution, and then when it hits higher probability,
and it goes
then it follows the shape. That's cool. All right, that's a nice
Beautiful
explanation.
That's story time, but it might be correct.
No, it is.
Dahlia, you had something to?
No.
Okay, good. Anyone else break it in an interesting way? Okay, let's carry on. So when I showed you this to start, obviously I'd done this myself. I'd gone through and found good step sizes that gave good results. So there was some tuning in the background that I kind of skipped over. But now you see what it takes to make Markov chain Monte Carlo work. You have to do some tuning. Okay, but with a well-tuned sampler, it looks like we made a nice, precise measurement, right? Those contours were really good. Our next step, though, is to check the model for accuracy. All of that inference was assuming a given model. So now let's step back a bit, and before we publish, let's worry a little bit about whether our model was good. So we need to check the model. So let's think about this a bit.
You must not be applying for a job.
Sorry, what's that?
But you must not be applying for a job. You just have to take this extra step.
Oh, I must not be applying for jobs because I'm bothering to check my models. Right. Okay, so two properties that make a model good. One is accuracy. So Andy Muller the other day spent most of his time talking about accuracy, cross-validation strategies, like always, is the model accurate? How accurate is the model? There's another good criteria for goodness of model, which is efficiency. We'll talk about that towards the end. Okay, so accurate models generate data that is like the observed data. That's what it means to be accurate. And also, if you imagine taking future data, you can imagine having a model that would be good at predicting future data. Brendon.
As an ideologue, I must insist that you point out that you're now outside of phase with the things that you're adapting.
Okay, there was some ideological comment from Brendon, which we will skip over. Totally ignore. Because what I'm about to show next is, I think, hopefully, Brewer compliant. But do when it comes up, you should say, "Hang on a minute." Okay.
I'm happy with these techniques if you interpret.
Let's see the techniques first, and then you can comment in real time. So, visual model checking. The first thing that's useful to do is to show the predictions of our model in data space. That is, to make, for each M and B pair, make the straight line that corresponds to, and look at it in the context of the data. So that's what this does. All right. So most of those lines look pretty good, right? You can see that the lines that came from the samples from our burn-in period, they're the ones that don't have high posterior probability. But you can see many lines in the middle that are all plausible fits through this data. So this is what you get for taking the trouble to characterize a posterior PDF. You get a sampling of plausible models given the data. It'd be nice to see more plots like this in talks. What's it?
Yes.
Oh, right, some agreement from the floor.
There are some handy matplotlib tools for plotting that not as a sequence of lines, but as a distribution, as a polygonal distribution.
As a shaded region.
Oh yeah, a shaded region. The shaded regions are nice, right? But they've lost information because you no longer see that everything that went into it was a particular straight line. And you can be fooled when making that kind of plot into thinking that your model is actually more flexible than it is. So I guess I like just visualizing samples. You could also animate this and step through and look at all the sample straight lines like that as a movie. Okay, we can do something else beyond visual checking. You should probably do visual checking first because you learn a lot from looking at that plot. We learned that our model was pretty sensible. But we can also go one step further and we can ask how similar is our observed data set to not the posterior model predictions in data space, but replica data sets that we draw from our model sampling distribution. Right? We have a complete model that I showed you yesterday, that PGM that describes the forward model. We have a model that can generate data, and so we could draw replica data sets that should be similar to our observed data set if our model is true. So we could do that. We could make a large sample of mock data sets, each one corresponding to a particular M and B pair and a particular noise realization. And that would be a replica data set that would be plausible given our uncertainty about the parameters. And so with those replica data sets, we can summarize them and compare them to the same summary of the real data set. And that's what the posterior predictive model check is all about. So there's some math here that describes that in some detail, but basically we're looking for an informative test statistic, summary statistic, that we apply to the data, and we can also apply to all of our replica data, one set at a time. And then we can look at the distribution of summary statistics coming from our model and ask, where does our one data set, the only one that we ever get, where does that fall in that distribution? And if it's an outlier, we should be worried, because it means that our model is consistently, given our uncertainties, predicting data sets that don't look like, as defined by the summary statistic, don't look like our real data. So let's do that.
It sounds like straight frequentism.
It sounds like straight frequentism. What were the parts of the sentence I just said that didn't sound like frequentism? I said posterior PDF. I said uncertainty in parameters. That we're not just picking one point in parameter space and making replica data sets. We're considering all plausible points in parameter space. So that's the key difference. But the action of making replica data sets sure does sound like frequentism. So it's something that where we can connect with our frequentist colleagues. We have this in common, that replica data sets are useful when checking models. Okay, so here's a whole bunch of test statistics that I tried to write down. Some of them work well, some of them don't. I'm not very good at designing test statistics. We should try and improve this, but Elisa suggested a very good one yesterday. She said, what about the correlation coefficient? In fact, it wasn't Elisa. We had a question from Twitter. Who was it on Twitter that suggested this? Tangentially. I can't remember who it was. Thank you, Twitter, for pointing out the correlation coefficient and asking for an opinion on it. And I said the correlation coefficient is a useful summary statistic of the data. And so here it is, given a new lease of life, coded up as a test statistic for posterior predictive model checking. So here's the formula for Pearson R correlation coefficient. It's a function of x and y, the data on our plot. So it summarizes the data, and we can look at the posterior predictive distribution for the Pearson R coefficient. And then ask, for our one true Pearson R coefficient that came from our observed data set, where does that fall? So that's what I'm going to do. Here we are. So let's unpack this a bit. This is a histogram of test statistic values. The test statistic is the Pearson R correlation coefficient. So we've got Pearson R, a histogram of Pearson R over our replica data sets. That's the blue histogram. And then the black dashed line is our one, the only data set we have, the Pearson R correlation coefficient for our one data set. And you can see it's right in the middle. So according to this test statistic, our model is pretty good. It consistently gives us correlation coefficients that match the data that we observed. We shouldn't be too surprised about that, because our generative model is a straight line that imposes correlation. So the test statistic here is pretty similar to the one that we were using, that is the log likelihood. It's not the same, but it has similar characteristics. So we can quantify a bit more. We can ask, what's the posterior probability for the test statistic of our data being greater than the one we observed? So that's this P of t greater than T of d, given the data that we use to get the posterior PDF, and it's some intermediate value. If this was bigger than, what's the standard number? 0.05, 5%? If this was smaller than 5% or bigger than 95%, we should be worried.
So, Phil, could you explain a little bit? This test statistic still seems pretty broad, since correlation coefficient goes between 0 and 1, or minus 1 and 1. So this seems pretty broad. Would a good test statistic be a little bit more confined, or would you say that it just matters that your true value is somewhere within the range of your test statistic and not outside of this confidence?
So it's the second one. That the main thing that matters is where is the observed data, the black dashed line, where is it in relation to the blue histogram of over replica data sets drawn from plausible models? What's the problem with this summary statistic for our problem is that it's too similar to the one that appears in the likelihood function. A better test statistic, a more discriminating test statistic, would probe aspects of the model that we hadn't been doing previously.
What about just asking what's the likelihood of the points?
We're coming to that in a minute. The likelihood of the points is a function of both data and parameters. At the moment, I'm just doing test statistics of data, but we'll come back to that thought. So I find it hard to design test statistics. There's some skill involved, but I think it helps, before we answer your question, but I think it helps to go back to this plot and ask and look at it and say, well, what is it we're not capturing, or what might we not be capturing, and then try and design a test statistic that probes that. And so maybe here we might look for something that maybe tries to capture this hint of curvature like this. Now I don't know what that test statistic would be, but presumably we could write something down that would be like Pearson R but curvy, or something. Or maybe we could just look at how well we do out here compared with how well we do out here. Brendon?
Don't worry, I'm just troubling.
Okay, good.
The Pearson's correlation coefficient has a sampling distribution from frequentist theory.
Mm-hmm.
Is that what comes out, or if we were frequentists and we did just that to check if our model follows or if our variables are correlated, would we get the same?
All right, so the question is, Pearson R in frequentist classical statistics has a sampling distribution. Are we doing the same thing? We've almost reached the limit of my knowledge of classical statistics. I guess that my answer would be similar to the one I gave Andrew, which is it can't be because we're doing this additional step which is allowing for all plausible models. We're not focusing on a particular estimate. But maybe Kyle could comment more on that if he's in the room.
Yeah, I didn't follow the entire discussion well enough to know that I can. I don't know. One is that the sampling distribution, you need to assume what you have a test statistic, you need to assume what's producing the data. So like, it's not like there's a general purpose sampling distribution for a test statistic that you can look up in a book usually.
Good. So there we agree that there isn't in general, there isn't a standard sampling distribution that you can look up in a book.
Right, and there's
special
cases where you can kind of, there's some generic
there are
statement.
special cases, right? But in general, your model won't fit those special cases. Yeah.
But that's not true for the correlation coefficient, right?
Right, and I'm just making there are lots of special kinds of test statistics we've been taking generally for lots of different distributions.
But in this case, like, there are these things about the correlation coefficient, but I don't think they work in the case where you fix the y values.
Right, because so the point there was that the other thing we're doing is considering fixed y, in some sense.
If you wanted to look for curvature, so imagine you were looking at. I feel like this stage in a data analysis is where you look at your results and you go like, are they okay? And so say you're worried there's a little curvature, then what I would do is project the points onto a parabola.
Project the points onto a parabola.
Projection of if I'm worried about curvature, I'd make a parabola. I project the points onto a parabola, and then ask, what's that projection?
Okay, I like that test statistic very much. The idea of projecting the points, the data, onto a parabola that presumably we just guess, and then asking how well do they
y
do.
equals x minus median x squared, and just ask for the mean value of that over the data.
Transform the data, do it. Okay, and the thing I like about that is that it implies you're thinking ahead to a possible alternative model, which is that we don't have a straight line, that maybe we actually have a quadratic function.
I mean, on that side, I would just, again, you do have a model in mind, so you can just make it, you can have the curvature be a parameter, and then you can just fit the parameter and look to see, like, what's the hypothesis test that curvature is 0.
Yeah, okay, so we could expand the model to include another parameter and then go ahead. Okay, let's keep going. Where did I get to? Here we are. Okay, so there was a question of, can't we just use the likelihood? And I said, well, it's a function of parameters and data. So in the case where we have that situation, it's called a discrepancy measure rather than a test statistic. It's a function of d and theta. And there we can ask for the posterior predictive distribution or posterior predictive probability for the discrepancy measure being greater than the discrepancy measure calculated with the real data. So, a good one perhaps is reduced chi-squared, or it could be log likelihood, but we kind of already did that, so let's do reduced chi-squared. They're so similar it's going to work out the same. But anyway, here is a test statistic that people love to use. You see reduced chi-squared in papers all the time. Here it is being given a new lease of life in posterior predictive model checking. So we write that down. Ow. I just got cramp. Ow. Okay, so we'll go ahead and calculate this. And here is a scatter plot. On the x-axis is the observed discrepancy. That is the reduced chi-squared for our one data set that we observe, and the samples are again posterior samples, so drawn from all plausible models, where we compute the reduced chi-squared for each plausible parameter value. And then the y-axis is the same thing, but now we're using the replica data set rather than the observed data set. And so if this was a good model, then you'd have scattering either side of the dashed line. And so what we can do is we can count the number of samples above the dashed line and count the number of samples below, and that will tell us the probability we're after. And so we can make a histogram of these differences and end up with this plot. And again, we see in this case, for this discrepancy measure, the observed point for our one data set is in the, let me restate that. The interesting thing there here now is how asymmetric is this distribution, because we were counting points either side of the 45-degree line.
It's possible that you don't have any samples on one side of the line with this particular data set?
So remember, we all have different data sets because we all ran the generate data differently. So you might have got one. Oh yeah, show that to everybody. Rutger got lucky. So you have a data set where it happens that the your model is a particularly bad fit. So can we see, actually, can you show us the plot of the straight lines on top of the data? Ah, look at that. See how many points there are off and see how much curvature there is? All right. So, let's keep going. There was a good suggestion there. Kyle said, why don't we expand the model? We see curvature, so why don't we just, invent a new model and fit that? Alma.
This test also, could you use also this test even if your model is not linear on your parameters? So
Yes.
You can assign exactly the degrees of freedom, just like.
So good, interesting. So where we wrote the test statistic here, there was a number of degrees of freedom, right? This ln of y minus 2. At this point, though, I'm using test statistics just as ways of summarizing the data. So we could rerun this with some other real number in the denominator, or we could leave it out, right? Because we're not interested in the sampling distribution as in kind of classical theory. We're just trying to summarize the data and the model predictions in this discrepancy measure. So you have more freedom, and we don't have to restrict ourselves to things where there is analytic theories for sampling distributions. Now, we're limited here by my own imagination. I said I'm not very good at designing test statistics, but it would be interesting to try and come up with some good test statistics, such as the projected onto a parabola. Maybe there are other ones we could come up with that were also interesting, and that would pick out specific places where the model isn't doing a very good job. And so this is a matter of skill and experience, and I have little of either of those things. Okay, so let's expand the model, because we think we see some curvature. At least Rutger did. So let's serve Rutger here. So the suggestion was to add a new parameter, make it a quadratic function with this extra parameter q, which is the coefficient of the quadratic term. So we have to write a new likelihood. I didn't redraw the PGM for you, sorry, but you can imagine what that looks like. Here's the quadratic log likelihood. You see how there's this extra term here in the predicted data. And then there's the quadratic log prior, where the first prior, I'm just going to go ahead and use the same prior that we used for M and B in the linear case. But I have to tell you that because it's one of my assumptions. And then I also now need a prior on the value of Q. Now, when doing this, I called this notebook straight line, right? So I took the data expecting this to be a straight line. I had some experience perhaps that I was doing this experiment. I was kind of expecting to see a straight line. So I'm a little bit surprised actually at this point that you see curvature. So that is to say that I'm not expecting the value of Q to be very large. So I'm expecting Q to be small, and I actually don't know whether it should be positive or negative at this point. I just know of it as a perturbation. So I'm going to go ahead and assign a prior that reflects those set of beliefs. So I'm going to choose a Gaussian centered on 0 with some small width, just to fit for a small perturbation. I don't want the perturbation to get too large because I don't believe that that's the case.
But you're pivoting very far from x equals 0, right?
Yes.
So though Q might be small, it has a kind of weirdly unpredictable effect on M and B because M and B are very far, like the intercept is very far from your data.
Yeah, so let's hold that thought and you'll see it in a minute. You'll see that when we do this fit, M and B are going to change.
Because if you really know the quadratic term is going to be small, you might parameterize it not as qx squared, but as qx minus median x squared.
Yeah.
You know what I'm saying?
Yeah. In fact, we should come back this afternoon to how to parameterize this better and see whether we can get some of the funny results that are going to come up in a minute to go away. Okay, so let's execute this. Quadratic log prior, log posterior. And now we need to set up the Metropolis Sampler again. So we need to initialize it with a particular q theta here. Here's the parameters q theta. And the limits, I have to pass those. And then the step sizes I have to set. And then I'm going to ask for 10,000 samplers. And I'm going to go ahead and run my Metropolis Sampler again. Good, 10,000 posterior samples drawn. And then let's again look at the traces. So different behavior this time.
Whoa, not converged.
Not converged. All right, let's keep going because we're running out of time. Let's look at the corner plot. Now we have 3 dimensions and we're looking at all 1 and 2D. If it was converged, these distributions would tighten up. So it is going to be worth our time tuning this in order to get better convergence. But notice, if you remember, M used to be small and now it's large. Because in this model, we're going from something straight line like that. With the curvature, it's going to make the curve go like that. And to fit the data, we're going to have to steepen it so that it can then come down again. So the gradient is now larger than it was before. And the intercept is different too. Lower than it was before. But if this was tuned, and it was when I had a different data set, it's relatively precisely constrained, and this will get better if we tune it better.
Question. For Q, it says that the average is 0.
Yeah, and
but on the histogram, it doesn't.
Yeah, okay. This is a typo from the way that we're formatting the numbers to put it above the thing. So this is an issue, actually. We should issue this to Corner.
I think there is a format keyword argument.
We should issue this to Phil to use
It's an open source project that accepts pull requests.
Yes, exactly. Okay, so this is just numerical error. If you look at the plot, you can read off the values. So again, this is over the plus or minus 3 sigma range of the Gaussian prior. But you can see that we're measuring Q here. This is significantly narrower than the prior. So we are making precise inferences. They're not accurate yet because our MCMC chains haven't converged. But with a bit of tuning, that could happen.
What was the prior?
The prior for Q was Gaussian centered on 0 with width 0.003. Okay, so we got to go through and check, or we get to go and check this. Here's the visual check. Maybe you like this better. What do you think?
Howdy.
Goes through more points like that. Okay. Now, if we look at the test statistic, this is the discrepancy measure. Where again I'm using reduced chi-squared, and look, I put the 3 in instead of the 2 for the degrees of freedom. And so let's look at the distribution, and here it's somewhere in the middle still, but different from last time, not as central.
But you're not converged.
But I'm not converged.
This isn't really valid.
Yeah, so I hope this would move more centrally. So we should tune it this afternoon and look for that.
But if you just took out median x.
Yeah.
But I think it's just a problem. I mean, in this case, with the points that we have, because minus looks like converged. I see also his.
Ah, good. What do you see when it looks like it's converged? What happens to this histogram? Can you show it?
Yeah.
Oh, look at that. Look at the dashed line right in the middle of the distribution. So this model check, remember that when we did this with the straight line, we had a similar result. The dashed line was in the middle. What that means is that this test statistic, reduced chi-squared, isn't very discriminating. It's not very powerful when applied as a posterior predictive check. So there's two ways we can read that. One is maybe we should go and design a more powerful test statistic. Another one is that it's less powerful than it would have been in the hands of the frequentists, because we are looking at all plausible models.
Why are you saying it's not powerful? What were you expecting other than what we showed?
Because if it was the case that we could discriminate quantitatively with the power of statistics as well as we could by eye, looking for curvature, then we should see that as the dashed line being towards the wings of this distribution.
Why?
The distribution
I
for
don't
some
understand
test
why.
statistics.
This is a perfectly good model. And in fact, you generated the data with this model.
Sorry?
You generated the data with this model, so this model should be confirmed.
Wouldn't you see it in the wings of the linear distribution and then
Yeah.
close to this?
Yeah, so maybe that's the confusing thing about what I'm saying. If you think back to the blue histogram,
Yeah.
there a good test statistic might do better and equally well as our eyes at discriminating against the straight line model.
Got it. Understood.
Actually, this data wasn't generated with this model, but close enough. Have you looked in the code as to the generated code?
No, I assume you generated with a polynomial.
It's actually with the quartic, but with the third. No, not quartic, a cubic, but with the cubic coefficient set to 0.
I think you did it with the infinity polynomial.
Okay, so here's where I'm going to say something wrong, and I'm hoping Kyle can correct me in real time. Okay, so all the above discussion was about model checking, which is assessing the ability of our model to make accurate predictions. And we used replica data drawn from the model, assuming it was true, and then looked at the probability of getting a summary of the data given this assumption. So now I'm going to attempt to say something frequentist, and I'm going to get it wrong. So Kyle, frequentists when doing hypothesis testing would do, where they would assume the null hypothesis, H0, and calculate the probability of getting their estimators for the parameters by chance by studying the distribution of a test statistic over a large ensemble of replica data sets, which under certain assumptions would be a standard distribution. Did I get that mostly right?
Yeah, I mean, I don't think there's any reason for the last part, but yeah.
I guess it's because I want to give you an out. I think people have this idea that frequentism means looking stuff up in books, but it doesn't necessarily mean that, right? It's just under certain assumptions you get to do that.
But it's not exactly that. They're not getting the probability of getting the estimators for the parameters by chance. They're getting the probability of getting this data by chance.
Probability of getting the data by chance. Good. So let's edit this so that it's correct.
Under this.
Probability of getting the.
Well, it's the test, the value of that test statistic was greater than the third one. Yeah.
Okay, I'm going to need some dictation.
Yeah, you can just say more extreme.
More extreme value of the test statistic on the data.
Probability of getting.
But more extreme is kind of ambiguous.
You just can't put parameters there.
I can't put. Well, I put estimators for the parameters.
Some choices sign larger.
Just to remind ourselves that the frequentists are also working with models that have parameters. They just believe that those are true things that can only be estimated, not inferred using probability distributions. So that's why I put for the parameters there to remind us. But the estimators is what they're working with.
I don't know why you're using estimators for parameters if you're talking about hypothesis. Test statistics.
So I should just remove this entirely. Getting the test statistic, the summary statistic. Let's call it summary statistic. Or do I call it? No, I call it test statistic. They're the same thing. Okay. Getting the test statistic by chance.
Yeah, well, there's a more extreme or whatever.
By studying the distribution of a test statistic over a large ensemble of replica data sets.
Value of the test statistic, right?
And I don't think you mean by chance. You're talking about a probability. It's not like
Oh yeah, okay.
anything happening or something. You already specified your normal.
I think the reason I put by chance is because from the beginning you have in mind a lot of possible data sets. Like the way you're dealing with the uncertainty of what could have been if you'd done the experiment differently. In that framework, right, yeah.
And you have confidence interval, like the probability of one data point is always 0.
probability of getting at the statistic right.
Right. So So this needs to be a probability of getting the test statistic larger than.
Yeah,
That the
exactly.
confidence interval contains the true statistic.
Or whatever.
Right. But in hypothesis testing, I guess we have to say larger than some p-value.
No, larger than
Ah.
Larger than the observed one.
Larger than the observed one. It's so hard for me to write down frequentist statements because I think like a Bayesian.
You're just not used to it.
I mean, you're not going to compare test statistics to a probability. I don't know what I'm saying.
It's also hard for me to do things live.
That's the hard
Have I got it right now? Calculate the probability of getting the test statistic larger than the observed one by studying the distribution of a test statistic. How's that?
Yeah, I mean, it's fine. I think the sentence is less awkward if you would be assuming the null to the end, you know? So, you know.
Oh, but I always want people to state their assumptions in advance. So that's why I've got it at the beginning.
But it's just sort of, yeah, but it's,
I'm willing to compromise
Maybe
my
2 seconds.
linguistic style for that.
but
I've-
it's still, but it just, I think it's more than linguistic style, because it looks like, I'm going to assume the null hypothesis, great, and then you're going to do some operation, right? But
Yep.
the operation that you're doing, you know, maybe it'd be like, if you say, assuming the null hypothesis,
Or
would be
condition.
right? It just said, it looks like logically disconnected statements, like, step A, I'm going to assume the null, step B, I'm going to calculate something. But
But
the
the
thing that you're
calculating-
calculating requires that you're making that
It's the
assumption.
calculation that is the functional assuming of the null.
I don't see what's wrong with what I've written.
It just,
Okay.
it's not, it looks like it could be too disconnected.
If you interpret it the way that you want it to be interpreted, then it's correct. But it's just
Okay.
like if you didn't know what was being made, it's not necessarily clear that calculation was made.
Okay, but operationally, I think you do this. Right? You assume null hypothesis and then you calculate.
Well, the assumption of the null hypothesis is the calculation.
Yeah. Okay, so with the Bayesians, though, we're in this model checking exercise, we're assuming the alternative hypothesis and calculating the posterior predictive probability distribution for the test statistic given the data, marginalized over the model parameters. And in general, this distribution will be non-standard, just like it is for the frequentist, actually. But we can often draw samples from the posterior PDF anyway. That allows us to cope with uncertainty in the parameters that have this PDF associated with them.
Okay. Well, I mean, if you're trying to draw some sort of comparison between the frequentist and the Bayesian with the null and the alternate part of it, I mean, one thing that's important is that normally the frequentist the design of the test statistic is based on the alternate. So it's not like
it's that
getting
the
the
statistic is designed to point away from H0.
In the direction of H1.
Yeah.
And in fact, there are ways to find the best possible test statistic if you have a generative model.
And if you have an H1.
If you have H0
Which
and
they do.
H1, there's in some sense a best statistic.
So here H1 is the, okay. So I guess to really make this symmetric, I need to mention the null hypothesis in the Bayesian one. Anyway, I hope that was more elucidating than confusing, but we should continue this afternoon for people who are interested in the difference between the two frameworks. I'm going to carry on in Bayes in the next few minutes because it's almost coffee time. Okay, so I have a hack suggestion here. So far we haven't talked at all about cross-validation, but it came up in the machine learning tutorial. And if you remember, what was going on there was that the one data set they have, they're splitting into chunks and training on some fraction and then testing against the rest. Now in Bayesian inference, training means learn the model parameters, calculate the posterior PDF. And then there's prediction. Once you've got that, you can do that with the posterior predictive distribution. So we ought to be able to come up with a way to use cross-validation for Bayesian inference. I didn't have time to work through what that was, but I think, Hog, maybe you've done it in practice. Mm-hmm. And so one thing we could do as a hack, if we had another week, would be to code into scikit-learn or inherit from scikit-learn or do something with scikit-learn that uses their cross-validation technology, but instead of having a linear one of the models that's provided in scikit-learn, like random forest or linear SVC or any of these things, we could build in a Bayes model that produced an a score, just like the scikit-learn models do, which we could then use in cross-validation. And it would be interesting to compare the results from that with the posterior predictive model check, which is doing something slightly different. And is also different from the thing that I need to show you next, which is the model comparison the Bayesian way via the evidence. Okay.
The interesting thing is if you use as the score the probability of the left out data and you loop over all the left out chunks in that way, the integral, the total operation you looks unbelievably similar to the Bayesian evidence.
Does it? Interesting.
Yeah, and yet it is not the same.
But it looks a lot like it.
It looks incredibly similar, but it's not the same. If it was the same, it would be trivial to do Bayesian evidence because this would be a way to do it. But
Maybe it's close enough for our purposes.
well, it's interesting. So Jake and I tried to write a paper about this, but we couldn't actually write down any sensible set of assumptions in which they were identical.
Okay, but even just seeing the comparison between Bayesian evidence that we're going to see now and the results of cross-validation would be interesting.
Yeah.
That could be a tiny little breakout this afternoon, maybe.
2-minute breakout.
2-minute breakout this afternoon. I'd like to see that. Okay, so model comparison. We talked a lot about this last night in the debate, and I have to go through quickly with this. Hopefully you picked up some things yesterday. But so far we haven't talked about this normalizing constant, as we were referring to it, in the denominator of Bayes' theorem. That is the probability of getting the data given the model we've assumed to be true. So that's the evidence. We're calling it the evidence, also known as the fully marginalized likelihood, or FML. And if you make a ratio of the probability of getting the data given one model and the probability of getting the data given another model, that ratio is called the Bayes factor, or the odds ratio, or the evidence ratio. You see that in the literature.
Not the odds ratio. The odds ratio takes into account the prior the two hypotheses.
Beg your pardon. You'll see why I think of it as odds ratio in a second. So let's just remove that. Forget that, Bayes factor or evidence ratio. Okay, so this quantity, you can see by looking at it that it's similar to a likelihood ratio, popular in classical statistics, but it's been marginalized over all plausible parameters. Like we marginalized, in order to calculate this, you have to do the integral of the likelihood multiplied by the prior integrated over the parameters for it to be a normalization for the numerator of Bayes' theorem. So that's how you calculate. You just have to do that integral. But what this integral captures is something, as well as the accuracy of the model, how well it can predict data, it also captures something about the efficiency of the model. So to see how that works,
Sorry, can you define efficiency in this context?
to see how that works, including the definition of efficiency in this context, it's helpful to look at this picture, which we saw last night in the context of David's crazy extreme cosine model, 3 parameters that can fit any scatterplot of data, the one that went like this through all the points. So here's the picture that we then drew. You remember we drew a uniform prior, and then we drew a spike at the parameters that gave a good fit to the data, very high likelihood, and then there was 0 likelihood anywhere else. Remember that spike? So that picture is similar to one of these pictures. I forget which one. It's like this one, but imagine shrinking this red Gaussian to a line, because the red thing here is the likelihood as a function of parameters theta, and the blue hat is my prior, and they're on different scales, of course, because the likelihood isn't a probability distribution, but the likelihood goes up to the peak value, which is Lmax, and the prior here goes up to its peak value, which is 1 over the difference in the min and max parameters. So it turns out for this problem, where you have this uniform prior and this Gaussian likelihood, if you do this integral, it turns out that the evidence is equal to Lmax, which is this point up here, multiplied by the fraction of this dashed box that is enclosed by red shading. And you can work through what I say in this notebook to see that that's true. But look at the dashed box, and then look at the area of that dashed box that is shaded red. That fraction, the red fraction, is the evidence in this problem. So now you can see graphically what it means to have high and low evidence. So on the right hand side is very low evidence. You can see the prior is offset from the likelihood in parameter space. and the fraction of the dashed box that's shaded is very small. So this is a low evidence situation where the prior and the likelihood are mismatched. And then in the middle here you have prior and likelihood very well matched. This is a very high evidence situation, interestingly. And then on the left hand side is something more usual, where you have sort of intermediate evidence with between prior. Now imagine what would happen if we made this blue hat on the left hand side very, very broad. Then we'd be in the situation we were in last night where the likelihood was narrow compared to the prior. And that would be a low evidence situation, because you'd have an enormous blue dashed box with a very small area enclosed by red shading. So it would be a low evidence situation.
So one of the points that I would make if we were going to debate whether we should calculate this thing is that in this case, so you have this flat prior here. Now imagine you've made the blue box much, much wider.
Mm-hmm.
None of your posterior inferences would change at all.
Mm-hmm.
In this case, your posterior would be exactly the same because you're
Right.
multiplying a flat thing by this likelihood.
That's right. None of your, I'm going to repeat for the people at home.
Yeah, good.
So if we did make that prior much wider, none of the posterior inferences for parameters would change because they're conditioned on the model assumption. And the model assumption includes a very broad prior.
But I'm saying as you change those assumptions, you don't change your posterior.
That's right.
So it's conditioned on those assumptions,
Yeah.
but it actually isn't affected by those assumptions.
Mm-hmm.
But the Bayesian integral is very strongly affected by
Yeah.
those integrals.
So it's when you go to secondarily after the fact in some cases, or during the process in others, when you calculate the evidence integral and compare it to some other evidence for some other model, then you get to learn about the relative efficiency of those two models, where efficiency is basically defined by this additional Occam factor. So you see here I said E was the product of the L max and the F, the fraction of the volume. So when this F is small, I'm saying that's low efficiency. So F is efficiency here.
But the point I'm trying to make is that if as a user you just set these two ends of your prior relatively arbitrarily, then the value for this integral you will get will be relatively arbitrary.
Exactly. So the people at home, if you set the limits on your prior arbitrarily, then the value of the evidence will also be similarly arbitrary, which is completely consistent with the framework we're working in, which is one for propagating prior beliefs, updating them into posterior beliefs. If you write down a prior that does not reflect your prior beliefs, then you shouldn't expect the evidence to reflect your posterior beliefs.
So one thing you could say, so people yesterday were saying, well, what prior should I choose if I don't know? And some say, oh, well, I could do this or I could do this. Well, it's a different model to choose this prior or this prior. So what you should do is choose every possible choice for the prior you want, and then use this to mix them. And guess what you will learn?
What do you learn, David, in that?
You will learn that your prior is your posterior. The mixed model will have posterior. The prior is your posterior.
What?
Sorry, what?
I believe that's what will happen. If you consider every possible prior.
If you consider every possible
Those are
prior
different models.
and
They
mix
can
them
be
together.
compared by model comparison techniques that the Bayesians propose. And I think you get.
I
It's
don't
very
know what
obvious.
measure to use on the space of all possible priors.
If you
You
you're
have
happy
to put probabilities on them.
if you can put a probability, if you can put a measure on the set of possible priors, then that's equivalent
Well, you
to
have to.
specifying.
You do this all the time, right? Because you have two different models that have slightly different
So
priors.
that's equivalent to choosing a specific prior.
And when you do the averaging,
It is. I agree. But
there's also something that came up yesterday in Brendon's lecture. When you do the averaging, when you apply the sum rule for probabilities, there is this additional term, right, which is the bit about exclusivity. So that has to be taken into account. Maybe that might be a factor in this derivation that we might
no,
do.
but that's not true. In the model comparisons, there's no claim that the models aren't nested.
I see. When doing the odds ratio.
Yeah.
I see.
So there's some absurdity here that bothers me.
And I think it's connected to this sum rule. But I thought what you were going to say was, if you say I don't want to assume hard limits to my prior, I instead want to learn them from the data, well then what you should do is you should parameterize them as part of your model and assign a prior to those new high hyperparameters, and then learn those from all the data you have. And that's the hierarchical model we were talking about on Tuesday.
And that'll give you the same results as using something that's heavy chaotic like the Pearson distribution.
So in general, I think it's better to think in terms of hierarchical modeling than quantitative model comparison and averaging in general. But there are some cases where it's difficult to do that, and so it's useful to carry the evidence around with you and compare one with another. Okay, one other point to make about this, that there's this F efficiency factor, but it's also there's this Lmax appears, like the value of the likelihood at its peak appears in this little expression. And Lmax, for the case of a Gaussian likelihood function, is e to the minus misfit function, which is to say that the evidence is exponentially sensitive to goodness of fit, or rather, or also badness of fit. And it's linearly sensitive to this efficiency, to this prior volume. So sometimes objections are raised which are, well, suppose we made the prior really, really large, we can make the evidence arbitrarily small. It's easy to make the evidence for a different model beat that by having it fit the data better. So the easiest way to make the evidence go up is to have the model predict the data better. So accuracy is prized more highly over efficiency in the evidence. Okay, calculating the evidence real quick before we have coffee. There are practical ways to calculate the evidence during the process of sampling. You should look up nested sampling, parallel tempering, thermodynamic integration. In general, it's hard though. You have to spend more time sampling because you're trying to do an integral over the prior. So you have to spend more time understanding the prior rather than focusing on the posterior. So that's the price of calculating the evidence. You have to spend more time paying attention to the prior. It turns out for simple problems like ours, you can calculate the evidence using a particular sampling method that I'm not sure I ever recommend you use in practice, but it's fun to try it out, called simple Monte Carlo. And so here's a last sampler for the morning, real quick, just to show you how this works. What we were doing earlier, we said that all inferences of interest were integrals, or at least I said that, and we're sampling in order to do integrals. And we do it by approximating things like the posterior mean here by sums or averages over posterior samples. So theta bar is the average theta parameter that you've sampled. Now, suppose we replace our posterior PDF with Bayes' theorem, which has the sampling distribution and the prior and this evidence constant, which I'm calling Z. So we could write that posterior mean integral like this, and then we can approximate it with posterior samples. That's what I drew before. But now we can replace the posterior with our likelihood times prior divided by evidence and ask for the posterior mean as an average over the prior samples. And you can see now that in this sum it's now become a weighted average. And it's weighted by the value of the likelihood at each sample position. So if you just want to get the posterior mean using prior samples, you just calculate the likelihood at each sample value and then do this weighted average, where the weight is exactly equal to the value of the likelihood. Now, to compute the evidence, imagine the same integral, but we remove the theta, so because we're interested not in the posterior mean, but the mean likelihood over the prior, and then rearrange to get z, and it's just the average of these likelihood factors over the prior samples. So the procedure is draw a lot of prior samples, calculate the likelihood function at every one of them, and then average those likelihoods together, and that's an estimate for the evidence. Okay, so we're just going to go ahead and do that, and we'll do it for our quadratic model and our straight line model. So here I am drawing a large number of prior samples and doing everything I just said. We should look at how well this actually works by visualizing the corner plot. So here we are in blue for the straight line model. Works pretty well. These are posterior samples where I've made weighted histograms. You can provide weights to corner. Here's the core you see here. The weights are equal to the unnormalized likelihood for the straight line. Not log likelihood, but likelihood. And then we can do the same thing for the quadratic model. There's a question for coffee. It's going to be in green. Here it is. a better approximation than my unconverged MCMC, interestingly. And now we can compute the evidence. We need a new function for doing the average because we have to take care about the exponentiating things. And so here we have the evidence ratio for these two models. And I called it odds because I'm still using the wrong words. Evidence ratio.
How do we know how many digits of accuracy you have on those numbers? Because this might matter. In fact, they're fairly close, right? I can't quite
Right, good. So let's go back to engineering mode. How would you estimate the uncertainty on my log evidences? What would you do? What's the simplest possible thing you can do?
Standard error.
Standard error of the mean, which means you have to do it a bunch of times and average them together. Okay, so we could do that.
Or you can just extract from one.
Right, that's going into the weeds. I rounded them off because typically it's not more than a unit is hard to perceive in probability, in log probability. And you should read about the experience of the people cracking the Enigma code at Bletchley Park during the Second World War, who used Bayesian methods to do that. And they worked with evidences, calculated evidence ratios, and they worked figured out what units in log prob that they could perceive. And roughly speaking, rounding off to the nearest integer works is sensible for evidence ratios. And so in this case, for my data set, the evidence ratio in favor of my quadratic model and all of the priors I assumed for it is 4:1. Okay, so there are exercises to do if you want to play around with this and break it. But I just wanted you to leave you with this one conclusion relative to the model checking and accuracy that we talked about earlier in the week, which is that the evidence is giving you something qualitatively different because it's taking into account your prior beliefs as well as the likelihood, as well as focusing on the accuracy of predictions, the goodness of fit. It's telling you something about the efficiency of the model, how probable any position in parameter space was a priori. And that's not captured by these other methods and is interesting to think about at least. Okay, thanks very much for listening.